Alright, now we will continue our sample problem, and in this problem we'll be doing internal forces, or we'll be solving the internal shear and internal moment, and we are going to present that in terms of an internal load diagram. Okay, so this problem is again taken from the textbook by Timothy Philpott, Mechanics of Materials, and this is example 7.5. Okay, so we have this beam right here. It is a cantilever beam. So we have a free end right here, and this one is a fixed support. And this beam is subjected to a 19 kilonewton concentrated force, and we have a distributed force right here. That's 3 kilonewtons per meter. Alright, so the distance from point A to B is 2 meters, from B to C is also 2 meters, and from C to D is 3 meters also. Okay, so looking at the problem, this is actually a determinate problem because we have 3 unknowns, 3 reactions at point A, and we have 3 equations of equilibrium. So therefore, this is a determinate problem. Okay, so for the first solution is to draw the free body diagram and solve for the support reactions. Okay, so right here, so let's say we have this 19 kilonewton concentrated force, and right here we have a distributed force of 3 kilonewtons per meter. Okay, and if we want to take the equivalent concentrated force, this is just simply 3 kilonewton meters times the length. So this is 2. This is 6 kilonewtons. Okay, so in terms of the distance, this one is, right, so this one is 2 meters, and the distance right here, this is 6. Sorry, 2 plus 1. Okay, so this acts along the center, or along the midpoint of this load, so that is 5 meters. And our support reactions, we have, let's say we have AX, and we also have, let's say, AY, and we also have a moment, and I'll just write A sub M for the moments. Okay, so summation of what else? I think we'll just apply the summation of moment at A. So I'll take moments at A. So that means that since I have a concentrated moments right here, so that's going to be, let's say my assumption is clockwise is positive, so AM. Okay, because that's a concentrated moment, so I have to include that in the moment equation. Okay, AM. Okay, and then this force. So this force produces a counterclockwise. So that's going to be negative minus 19 kilonewtons. Okay, minus 9 times the moment arm of 2 meters. So 19 times 2. Okay, so sometimes I don't write the units just simply because I just want it to be clear, and just to remember that all the forces are in kilonewtons and all the distances are in meters. Okay, so this is 19 times 2, and then the next is this force. So this force, this is producing a clockwise, so this is plus, right? The value, the equivalent value, this is 6 times the moment arm of 5 is equal to 0. Okay, so therefore A sub m so AM is equal to this is 38, okay, minus 30, right? So this will be, and if you transpose this to the right hand side, what you get is AM is equal to 8 kilonewtons meter. Okay, then the next step is to apply the summation of forces along y is equal to 0. So if it's along y, then let's assume that the positive direction is upward. So this is A, right? So A sub y. Okay, so we have a downward right here. So let's say minus A sub y, okay, plus the positive 19, okay, plus or minus the minus 6 is equal to 0. Okay, so if we transpose this to the right hand side, what you get is A sub y is equal to 13 kilonewtons. Okay, and what else? If we apply the summation of forces along x, AX would just be 0. Okay, so now we have AX, we have AY, and we have the moment. So now let's draw the beam again, and then we'll make sections. This is A, this is B, this is C, and this is D. Okay, so I'll make a cut between A and B, and then we will apply the equilibrium equation to be able to solve the internal forces between A and B, and then after that we'll make a cut in this section between B and C, and then apply again the equilibrium equations, and finally we'll make a cut in between C and D and apply the equilibrium equations. Okay, so for now I'll just make here an arbitrary cut, and of course we have to show the reactions, the value of reactions. This is 13 kilonewtons, and we have a moment of 8 kilonewtons meter. Okay, so I just have to rewrite this 13 kilonewtons and 8 kilonewtons meter. Okay, so once I make a cut right here, then I have to expose the internal forces, and recall that the internal forces are composed of shear, moment, and axial, but for beams usually we only have shear and moment. Okay, so this will be my shear right here. So let's say this is my shear, and I'll also have a moment like this. Okay, and I'll just write m sub 1. Okay, so again, these are external forces, then these are support reactions, but when we make a cut, this will be internal forces. Okay, so let's apply the equilibrium cases. So summation of forces along the y direction. So we can see here that the shear should be in the upward direction. So what we'll see here is right? So V, that's actually negative V minus 13 kilonewtons is equal to 0. So we have V is equal to negative 13 kilonewtons. So therefore V is 13 kilonewtons and should be in the upward direction, right? So that's positive. Okay, and what else? Let's take summation of moments. So summation of moments at A is equal to 0. So this is my moment. I think I should just change this, or better, if we take moments, then we need to have some distance. Okay, so since this is an arbitrary cut, then we'll just write x. Okay, so summation of moment at A, we have a positive moment right here, so 8, okay, minus the concentrated moment, so minus m sub 1, okay, plus, since we have a positive, I mean based on this direction, but of course we have to take into account the negative. Okay, so when we take this direction, we have to take into the negative sign. Okay, so this is plus v sub 1, okay, times the value of x. Okay, v sub 1 times the value of x equal to 0. Okay, so since we have the value of v, this is negative 13. Okay, so we have 8, okay, minus 8 minus 13x is equal to, right, 8 minus 13x is equal to m sub 1. Okay, or m sub 1 is 13x plus 8. Okay, so this is an equation of a line. This one is a constant. So in other words, that the shear is just constant, but for the moment, it's a linear. Okay, the next step is to make a section from point B to point C. Okay, so right here I'll write the correct shear value. So this is 13 kilonewtons in upward direction, and we have a moment that's like this. So we have 8 kilonewtons meter. Okay, and right here we have an external force of 19 kilonewtons. And in this section, what we'll have is a force, a shear force, right? A shear force, let's say V sub 2, and we have an internal moment, M sub 2. Okay, so the distance, okay, from point A, let's say from point A to this load, this is equal to 2. And the distance from point A to the section cut, this is x. So if this is x, this is 2. This distance would be simply this would be simply x minus 2. Okay, so again we apply the equilibrium equation. So let's take summation of forces along y is equal to 0. Okay, so all the forces is 13 plus 19, so that's going to be 13 plus 19, right, 13 plus 19, okay, minus v sub 2. So v sub 2 is equal to, by the way, this should be downward. Okay, Okay, the reaction should be downward, right? Alright, so I'm sorry about that. This should be downward because the ones that we changed, the direction is the shear force, but for the support reactions it should be downward. Okay, so if that's the case, this will be 13, right? 13, negative 13 plus 19 because it's upward minus v sub 2 is equal to 0. So therefore v sub 2 is equal to 6 kilonewtons. Okay, 6 kilonewtons. Then if we apply the summation of moments at A is equal to 0. Okay, so from this point, from point A, we have a concentrated moment of 8. So this is 8. Okay, and then and this load will produce a counterclockwise, so 19 times the moment arm 2, and that's negative, minus 19 times 2. Okay, and then the shear force will also produce a moment, but this one produces a clockwise moment, and this one will be v times x. Okay, so plus v times the value of x. Okay, and what else? There's also a concentrated moment that's counterclockwise, so minus m sub 2, okay, is equal to 0. Okay, so if I put this moment in the right hand side, what I get is m sub 2 is equal to the value of v, which is 6 times the x. Okay, and this will be minus this is minus 30, right? So again, this is a concentrated, I mean this is a constant function, but the moment is a linear function. Okay, then what else? Then the next step is to solve the or we'll have to make a section between C and D. Let's write it here, 2 section A to B, and right here this is 3 section B to C, and right here is section C to D. Okay, so okay, so I'll make an arbitrary cut right here. Okay, and by the way, if I mean, since this is a distributed force, then we can also represent that in terms of its equivalent force. Okay, so this equivalent force is just simply right, so this distance is still 2 meters, but the distance from this point, from this midpoint, okay, this to this, to point A, this is x. So therefore, the distance right here is just simply x, x minus 4, right? X minus 4. And the value, if this is 3 kilonewtons per meter, this is 3 times the by the way, let me write. Now the distance x should be from point A to the section cut, right? So this must be point x, I mean the distance x. So from point A to the section cut, and the distance from A to B is still 2 meters, the distance from B to C is still 2 meters, and this this one, this should be x minus 4, and the half of this is x minus 4 all over 2. Okay, so that's our distances. Again, this is x, this is 4, right? This is x, this is 4. So the distance from this point to this point, point C, that's x minus 4. And if we need the equivalent concentrated loads, that's going to be acting on x minus 4 all over 2, right? From this point, that's half of x minus 4. Okay, but of course, if we are taking moments from point A, then we should add plus 4. Okay, so I guess we are good to go. And if we apply the equilibrium equations, so summation of forces along y is equal to 0, then this one is negative 13, okay, plus 19, okay, plus what is this? This is 3, and also we forgot our internal forces. All right, so let's say this is m sub 3, this is v sub 3. So 13 plus 19, okay, positive 19, and this force is just simply 3. Right, so 3 times what is this distance? This is just x minus 4, right? So 19 plus negative 13 plus 19, okay, minus 3 times x minus 4. Okay, and what else? Our shear force minus v sub 3 is equal to 0. Okay, so right here, if we simplify, what we get is v sub 3. Okay, v sub 3 is equal to okay, we transpose this to the right hand side, is equal to negative 3x minus 4, okay, plus 6. Okay, and if we simplify this, we get 3x, okay, plus 12 plus 6. Okay, so this is negative 3x plus 18. This is our value of v sub 3. Okay, so you would notice that if there's there's a constant or a uniform loading, our shear value would be a linear function. Okay, compare that to these concentrated forces, our shear value would just be constant. But if we have a distributed loadings, it will change to a linear function. Okay, and then if we apply the summation of moment at A is equal to 0, this is a lengthy operation, but if you apply this, you apply properly the distances. So what you get is an equation that looks something like this. This is negative 1.5x squared plus 18x, okay, minus 54. Okay, so this is this one is a quadratic function. Okay, so linear, this one is quadratic. Okay, so now how do we plot this in the diagram? So now, so if we draw the shear and moment diagram, so let's use this another sheet of paper, and let's write down the support reactions. And so right here we have a 13 kilonewtons, that's concentrated loads downward, and we have this concentrated moment right here. This is 8 kilonewtons meter. Okay, so first is, by the way, when you draw the shear and moment diagram, it should be under this figure. Okay, so there must be a figure that's drawn here, and then this will be our shear and moment diagram. Okay, so for the shear, so at this point, at point A, we have a concentrated load. So that means that we have a negative 13 right here. Let's say this is negative 13. Okay, so negative 13. And in the section AB, we see that anywhere along the section, that is, the value of shear is 13, right? So that means this is going to be 13 up to point B. I mean, just before point B. Okay, so just to the right, just to the left of point B. Before this loads, the value is 13 kilonewtons. Okay, so this will be 13 or negative 13 kilonewtons. And then at point B, since there's a concentrated loads, it's gonna be 19, right? So let's check our B to C. So it says here that from section B to section C, we have a value of 6 kilonewtons, right? So therefore, this should be right here. So from point B to C, this is 6 kilonewtons. Okay, and from point C to point D, we have, from point C to point D, we have a linear. Okay, so this is negative 3x plus 18. So if we draw this line, what you get is something like this. Since it's negative, so the sloping is negative, right? So 6 kilonewton meters. Okay, so that's going to be our shear diagram. So for the moment diagrams, okay, so for the moment diagram, then okay, so let's start at point A. So at point A, it says that we have a clockwise moment right here. So this clockwise moment, this produces a positive. Okay, so let's say this is positive 8, right? And if we check right here, by the way, for point in section A and section B, so if we check here, we have a positive 8, right? So this is positive 8, and we have a linear function, and that's negative. So meaning that's a decreasing function. So from positive 8, from point A to point B, this will be a linear. Okay, and if you substitute the values of, let's say, 2 meters in this function, let's say you value x is equal to 2. You can also write that in terms of equations. At x equal to 2, then you can get a value of m. And let's write it here. At x equal to 2, m sub 1 is equal to negative 13 times 2 plus 8. Right, so 13 times 2. Okay, 26 minus 26 plus 8, so this is 18, right? Negative 18 kilonewton meter. Okay, so this is 18 kilonewton meters. So let's say somewhere right here. Okay, and from point B to point C, we have this value 6x minus 30. So if we substitute, let's say from x, x is equal to, let's say x equal to, I think x is equal to, we'll start right here, we'll check. So at x is equal to 2, 6 times 2, okay, minus 30, or 6 times, I think we'll use 6 times 4, right? 6 times 4. Okay, so our reference would be from this point. Okay, so at x is equal to 4, so we'll use m sub 2 is equal to 6 times 4 minus 30. What we get is negative 6 kilonewton meter. Okay, so what it looks like is also a linear, right? So this is, let's say this is 6. Okay, so this is linear, but right here you would notice that this is a quadratic, and you just have to substitute the value of x. Okay, so if you substitute the value of x, what you get is a quadratic curve. So the value right now is like this, right? So this is negative 18, this is 8, and what is this? Negative 6 kilonewton meters. Okay, so I guess that's all for now in this video, and in the next video probably we'll move on to our next topic, or add some more sample problems, maybe three-dimensional problems. All right, so that's all in this video.